Hi all, I'm James Pustejovsky from the University of Wisconsin-Madison. I'm joined by my colleague Martyna Citkowicz from the American Institutes for Research. Today we're going to share with you some work we've been doing on meta-analytic selection models, including a new package called metaselection. This work is part of a bigger project with several more of our colleagues involved, including Megha Joshi, Melissa Rogers, Ryan Williams, Josh Polanin, David Miller, all from AIR. And we are grateful to the Institute of Education Sciences and the U.S. Department of Education for funding this project. As usual, what we're presenting here today represents our own views, not the Department of Education or the Institute of Education Sciences. Our project is concerned with the issue of selective reporting of primary study results. By selective reporting, we mean when affirmative findings, so statistically significant results that are consistent with theory, may be more likely to be reported and available for meta-analysis than results that are non-affirmative or say in the opposite direction or are not statistically significant. And if those types of findings tend not to be reported, that creates distortions in the evidence base available for systematic reviews and meta-analysis. For typical forms of selective reporting, we expect that average effect size estimates may be inflated relative to the true population values, and that selective reporting can also create bias in estimates of the degree of heterogeneity of effects. This is a long-standing problem, and there's evidence from lots of different research areas across the social, behavioral, and health sciences that selective reporting can be a concern for systematic reviews. Now, you might think that's all well and good, but we've got lots of tools available already for investigating selective reporting, right? There's well-known tools like funnel plots or contour-enhanced funnel plots. There's a variety of different tests for selective reporting, like the trim and fill method, the Eggers regression. There's existing selection models. Why do we need more tools for investigating selective reporting? One of the outstanding issues with the available methods is that most of them don't really handle the type of data that comes up often in systematic reviews in the social sciences. One of the features of systematic reviews in social sciences that's very common is to have dependent effect size estimates. So dependent effects occur when a particular sample or a particular study reports more than one effect size estimate that should be included in the synthesis. So this might happen because we've got a study contrasting treatment and control groups, but that measures multiple outcomes, not just O, but O, P, and Q. Or similarly, if we've got a treatment control study that measures effects at multiple time points, we'll have effect size estimates for time 1, time 2, time 3, perhaps. Or if we have a study that includes multiple treatment groups or multiple control groups, we end up with multiple effect size estimates that are contrasting, say, treatment T versus control, treatment U versus control, and so on. These types of features are very common in meta-analyses within the social sciences, education, psychology, and related areas. And there's now well-developed tools available for modeling dependent effect size estimates, but those models don't really deal with selective reporting issues. They're good for summarizing effects and investigating moderators, but they don't account for the possibility that not all of the effects are actually available or included in the synthesis. There's only been a little bit of work about this recently, looking at how we can combine tools for dealing with dependent effect size estimates and tools for investigating selective reporting. There are a couple of tools available, but most of them don't work all that well. And there's really a need for better methods for estimating average effects that account for the possibility of selective reporting. So in this project, we're focusing on a class of models called selection models, or p-value selection models. And those models have been around for quite a while. We're extending them to accommodate dependent effect size estimates. Let me start by telling you a little bit about the basics of selection models. They have two pieces. The first piece of the model describes what we call the evidence generating process, as in what would be the distribution of effect size estimates before selective reporting occurs. Most models use a familiar model, like something like a random effects model, where each effect size estimate is distributed normally around some mean. There's some heterogeneity variance, we'll call that tau squared, and then there's some sampling variance, we'll call that sigma squared. The second part of the model describes the probability that an effect size estimate that has been generated is actually observed and is available for meta-analysis. Selection models assume that this probability can be affected by the p-value from the effect size estimate. We'll call that Pij. There's a variety of different models of this form. One well-known one is the Vevey-Hedges selection model that assumes that the probabilities follow a step function. So effect size estimates that have p-values that are statistically significant at the conventional level have some probability of being reported, but then effects with p-values that are less than that threshold may have some other probability of being reported. Maybe there are further thresholds in the model besides the usual significance threshold. Maybe there's a threshold based on whether the effect is positive or negative that could also influence whether the effect size estimate ends up getting reported. Another more recent model was developed by Citkowicz and Vevey, and it's based on a beta density function instead of this sort of stepwise selection model. So here, the probability that an effect size estimate is reported varies smoothly as a function of its p-value. And this sort of selection function can take on a variety of different shapes. The Vevey-Hedges selection model implies that the distribution of effect size estimates that we actually see in a meta-analysis follows what we would call a piecewise normal distribution. So if we could see everything that's generated, it would look like our usual normal distribution. But say that effects that are not statistically significant and in the theoretically expected direction are reported with less than certainty. So maybe only half of them that get reported. So the distribution of observed effects would look like the blue density, and the gray represents the effects that are missing. If further the, say, effects that were in the opposite direction of what's theoretically expected are reported with even lower probability, then each interval, it's piecewise normal, but as a whole, it's got this kind of funky, discontinuous shape. So we apply these models to data sets that include dependent effect size estimates. Our strategy is essentially to ignore the dependence problem and estimate the model treating each effect size estimate as if it were independent. So we're modeling the marginal distribution without trying to take account of the dependence structure. We examined two different estimation strategies. One is sort of the more familiar maximum likelihood estimation strategy. The other is what we call augmented and reweighted Gaussian likelihood. This strategy is inspired by work from Maya Mathur and Tyler Vanderweel who developed a sensitivity analysis that uses a similar estimation strategy. In our research on these methods, we compare both of these estimation strategies, find that maximum likelihood estimation is generally performs better. So if we're ignoring the dependence structure when we're estimating the model, we need to do something on the back end or after we've arrived at estimates to appropriately account for the uncertainty in the parameter estimates. We again look at two different strategies. One is robust variance estimation methods, which is a familiar tool for handling dependence in summary meta-analysis models. Robust variance estimation methods are kind of in this context, they end up being sort of a quick and dirty tool for assessing uncertainty. They don't work all that well. And so we also looked at a more refined technique that involved bootstrapping. And we bootstrap resample in a way that accounts for the dependence between effect size estimates that are generated from the same sample. So let me now pass it over to Martyna to give us an illustration of how these tools work in practice.
All right, thanks, James, for that thorough introduction into the model. Now I will be working through some examples to show you how the package works, including how to interpret results from the models. I will use the Lechman and colleagues' meta-analysis on color priming. In their meta-analysis, they examined the red romance hypothesis, which states that the color red enhances attraction. Now, if we run a standard random effects model that accounts for the clustered structure of the data, again, effect sizes clustered within studies, but it does not account for selective reporting, the overall effect is roughly 0.21. If we add a moderator, specifically design type, into the analysis, we find that the average standardized mean difference, effect size for studies with between studies, study designs, are about 0.19, and the studies within subjects designs are about 0.27. Now, if we look at a contour-enhanced funnel plot of the data, what we are looking at is our effect sizes on the y-axis and standard errors of those effect sizes on the x-axis. In the upper right-hand quadrant, what we see are positive and significant effects, and the non-significant negative effects are represented in the lower left-hand quadrant. You'll notice here that the orange studies, which represent the within study designs, tend to be clustered in that upper right-hand side of the plot. So we'll see what that means later on. Now let's try running the step function selection model on our data set. First, make sure to load the package, and then of course load your data set. We are loading the Lechman data set from the metadata package. We did some minimal data cleaning to tidy up the data, and then we can move forward with implementing the one-step selection model. First, you want to make sure you set your effect size and your standard error, specify the level of clustering. In this instance, of course, our effect sizes are clustered within studies. We input our data set, or specify our data set. We specify the type of selection model. So we are running the step function model with just one step at a threshold of 0.025. This model uses a one-sided p-value, which captures the significance level and the direction of the effect. We are estimating the model using the composite maximum likelihood, or CML, and for now we set bootstrap to none. So first, what you will see is a call to the model that you specified to run. That also tells you the number of clusters, number of effects. In this case, we have 41 studies with 81 effect sizes. So on average, about 2 effect sizes per study. So there is clustering. So what we see here from the mean effect estimates is that our average adjusted meta estimate that accounts for selective reporting is about 0.13, which is 45% smaller than the unadjusted estimate that we obtained from the previous random effects model, which was about 0.21. The large sample 95% confidence intervals using walled type approximations is about negative 0.14 to 0.40. Now this overlaps with 0, which thus means that the estimate is not statistically significant. The package also outputs heterogeneity estimates and selection parameter estimates. Our tau squared is about 0.08, which is very similar from the estimate from the standard random effects model. And then our selection parameter estimates are represented below. First, we have lambda 0. Lambda 0 is always set to 1, and it represents the likelihood of being published if for studies with p-values of less than 0.025. Now, relative to that, the value of 0.548 for lambda 1 indicates that studies with a p-value of more than 0.025 are about half as likely to be published than studies with a p-value of less than 0.025. So our confidence intervals for our lambda 1 are fairly high, suggesting that they are imprecisely estimated, and there's quite a bit of uncertainty about the amount of selection in our data set. Now, this is the large sample confidence intervals are not the approach that we recommend to calculating confidence intervals, but we will show you another approach. But before we get there, I do want to show you a plot of the likelihood of selection. So on the x-axis, we have our p-values, and on the y-axis, we have the relative likelihood of selection. So again, what you're seeing here is that with p-values that are about 0.025 or larger, those are about half as likely to be published than smaller p-values. Now let's try calculating our confidence intervals using bootstrapping. Now, bootstrapping does take quite a bit of processing power and time to run, so it can be helpful to turn on parallel bootstrapping, and you can use that using the future package as described here. We also recommend setting the seed to ensure reproducibility of your results. Now, most of what you see here is specified as in the previous example. What has changed here is that we now, instead of saying none for Bootstrap, we are setting Bootstrap to 2-stage now. So this is the recommended approach. The recommended number of Bootstrap resamples we set to 1,999, and then we calculate 2 confidence interval types. The large sample confidence intervals, which were calculated in the previous example, as well as the percentile Bootstrap confidence intervals. The first thing you might notice is that our effect size estimate of 0.13 does not change, nor do the heterogeneity estimates or the lambda estimate. What's new in this example is that we now have an additional column for the percentile Bootstrap confidence intervals. And you might notice that this confidence interval is quite a bit narrower than the one from the large sample. Now let's try adding the study design type moderator to our example. You can do this by using the mean mods option. Here we have set this to 0 plus design, which is the variable name for the moderator. When we specify 0, that allows us to obtain the intercepts for each study design. So now looking at the output, what we see are the estimates for our study designs. So for our within the subject study design, our estimate is roughly 0.11, which is 40% smaller than the unadjusted estimate we saw previously, which was 0.19. For the within study design, the estimate is about 0.20, which is 28% smaller than the unadjusted estimate of 0.27. Our task squared also decreased, but very minimally. Our lambda 1 also has not changed very much. It went from 0.548 to 0.533. Now, for the step function selection model, we can also add additional steps. So previously, we set our threshold to a p-value of 0.025. Using steps, let's try specifying an additional threshold at 0.50, which represents the effects in the opposite direction of the hypothesis. The results here present our estimates for our between and within subjects designs, and you'll see that these drop down even further than previously. Now, looking at the selection process estimates, we see that we have an additional lambda estimate. We have a lambda 1 of 0.476 and a lambda 2 of 0.307. Looking at our plot, what this means is that studies that have p-values between 0.025 and 0.50 are again about half as likely to be published than smaller p-values. On the other hand, p-values that are 0.50 and above are about a third as likely to be published as p-values below 0.025. Although I covered only how to estimate the step function selection model so far through our examples, our package also supports other models. These include the beta function selection model that uses the beta density to model the selection process, originally proposed by myself and Dr. Megha in 2017. The location scale meta-regression model proposed by Vichtbauer and Lopez in 2022. And an extension of the predictors of selection model proposed by Coburn and Vivet in 2015, which allows for models where the selection parameters can vary by study characteristics. Now, we might be biased, but we do think that adding the marginal step function selection models to your meta-analytic toolkit is worthwhile. So we do have a preprint that presents a thorough investigation of the step function selection model using a simulation study. And our simulation studies show that bias is low compared to existing selective reporting methods such as PET-PEACE. There is a bias variance trade-off relative to the standard meta-analytic model. However, employing bootstrapping, particularly the 2-stage cluster bootstrap percentile approach, leads to close to nominal coverage rates for the mean estimate. So you can download our package on GitHub using the following statement. Now, don't forget to set build vignettes to true to obtain our vignette, which includes additional information about our models, how to use the package, and includes lots of examples. Now, the package is under development, so suggestions are definitely welcome. Thank you all for listening.